Okay, real talk. Right now, while you're watching this video, your computer is doing something kind of miraculous. It's playing a video, running a browser, maybe downloading a file, checking for updates in the background, all at the same time, on one piece of hardware. How does it not just explode? The answer is two words: operating system. And once you understand what an operating system actually does, not just it's Windows or it's Mac OS, computing starts to make so much more sense. Let's get into it. Here's what we're covering today. We'll start with what an operating system actually is, and why computers in the 1950s were basically useless without one. Then we'll look at what's inside an operating system: the kernel, the file manager, memory management, all that good stuff. Then we'll get into processes, which is honestly one of the coolest ideas in all of computer science. And finally, we'll talk about what happens when processes compete. Things like semaphores and deadlock, which sound scary, but I promise are not. By the end of this video, you'll understand something that most computer users have no idea about. And honestly, that's going to feel pretty great. Let's go. Here's a simple definition to start. An operating system, or OS, is software that manages everything happening inside your computer. It coordinates the hardware, runs your programs, and acts as the middleman between you and the machine. Think of it like the manager of a restaurant. The kitchen has all the tools: stoves, ovens, knives. The customers want food. The manager's job is to make sure the right tools are used at the right time, orders don't get mixed up, and nobody's standing around doing nothing. Your OS is that manager. Now, the big names you've probably heard: Windows, Mac OS, Linux. Those are all operating systems. Interestingly, both Mac OS and Linux are actually built on something called Unix, which has been around since the late 1960s. So when you use a Mac, you're running software that has roots stretching back over 50 years. Pretty wild. But why do we even need one? To answer that, let's take a quick trip back in time. It's the 1950s. Computers are the size of rooms. They cost millions of dollars. And to run a program, here's what you do. You book the machine for a block of time, like renting a tennis court. You show up. You load your magnetic tapes. You flip switches. You press go. The machine runs your program. Then you collect your results and leave, so the next person can do the same thing. This was called batch processing. One job at a time, handled in batches. You'd submit your job along with a set of instructions called a job control language. The machine would process it, and you'd come back later for the results. There was literally a human being, a computer operator, whose job was to babysit the machine between jobs. Today, that role has basically disappeared, replaced by system administrators who mostly manage things remotely. The big limitation? You had no interaction with your program while it ran. That's fine for payroll processing, not great for, say, a word processor where you need to see what you're typing. So engineers invented interactive processing, where a program can have a back-and-forth conversation with you through a terminal. But here's the problem. Computers were expensive. You couldn't have one per person, so a single machine had to serve many users at once. Enter time sharing. The idea is almost elegant in its simplicity. Divide time into tiny slices. We're talking milliseconds, and rapidly switch between users. Each person feels like they have the computer to themselves, but really they're sharing it. This is called multiprogramming, and when it applies to a single user running multiple apps, we call it multitasking. Early time-sharing systems could serve up to 30 users simultaneously. Today, your phone does this for dozens of apps without breaking a sweat. All right, so we know the OS manages everything. But how? What are the actual parts? Let's break the OS into two big pieces: the user interface and the kernel. The user interface is exactly what it sounds like. It's how you talk to the OS. Old-school interfaces were called shells, text-based command lines, where you typed commands. Unix and Linux still use these, and they're incredibly powerful. Modern systems use a GUI, a graphical user interface. That's pronounced GUI. Icons, windows, folders, a mouse pointer. This is what macOS and Windows use by default. Inside the GUI is something called a window manager, which keeps track of which application owns which piece of screen real estate. When you click a button, it's the window manager that figures out which app you clicked on and tells it to respond. But the user interface is really just a pretty layer on top. The real action happens in the kernel. The kernel is the core of the operating system, the part that does the actual heavy lifting. Think of the kernel as the engine under the hood. The user interface is the dashboard. Pretty and useful. But the engine is what actually moves the car. The kernel has several key components. Let me walk you through the important ones. The file manager. This is the part that keeps track of every file on your storage device, where it's located, who can access it, how big it is. When you open a file, you're asking the file manager for permission and location info. File managers organize files into directories, also called folders, and folders can contain other folders, creating a hierarchy. You've seen this: documents, arrow, school, arrow, fall, semester, arrow, essay, .pdf. That chain is called a directory path. Device drivers. Your computer is connected to all kinds of hardware: printers, keyboards, monitors, hard drives. Each one is different. Each one speaks a different language. Device drivers are translators. Each driver is custom-built for one specific type of device. It takes a generic request, print this file, and converts it into the exact technical steps that particular printer model needs. This is why when you get a new printer, you install a driver. You're giving the OS a new translator. The memory manager. Main memory, RAM, is precious. When you're running multiple programs, the memory manager has to figure out who gets what space, make sure programs don't accidentally write into each other's memory, and clean up when programs close. Here's where it gets clever. What if you need more memory than you actually have? The memory manager can fake it using a technique called paging. It takes chunks of data, called pages, and swaps them back and forth between RAM and your hard drive as needed. The result is something called virtual memory, a larger, fictional memory space that your programs can use, even if it doesn't physically exist in RAM. The scheduler and dispatcher. These two work together to manage processes. But I'm about to dedicate a whole section to processes, so let's keep these in our back pocket for now. One more thing before we move on. How does the OS even start? When you turn on your computer, the first thing that runs is a tiny program called the bootloader, stored in a special non-erasable memory called ROM, read-only memory. The bootloader's only job is to find the operating system on your storage drive, copy it into RAM, and hand control over to it. It's like the opening act at a concert. The bootloader comes out, warms up the crowd, and then brings the main act, the OS, on stage. The whole process of starting up this way is called booting or bootstrapping. And now you know where that term comes from. Okay, this is my favorite part of the whole video, because this is where things get genuinely mind-bending. Let's make a distinction that sounds simple, but is actually really important. A program is a static set of instructions. It's sitting on your hard drive. It's not doing anything. It's like sheet music sitting on a shelf. A process is that program running. It's active. It's changing. It's a musician actually performing the piece. When you double-click an app, the OS doesn't just run the program. It creates a process, a living, dynamic activity with its own memory space, its own position in the code, its own little snapshot of the machine's state. That snapshot is called the process state. It includes the current line of code being executed, the values in the CPU's registers, and the associated memory. At different moments in time, you'll see different process states. Here's the wild part. Right now, your computer is running dozens of processes simultaneously. Not just your browser and music app, background processes for security, updates, system services. It's a crowd in there. The OS keeps a list of all these processes in something called the process table, a big block of info stored in memory. For each process, it tracks where in memory it lives, its priority, and whether it's ready to run or waiting on something. Ready means, I'm good to go. Give me the CPU. Waiting means, I'm paused, expecting something to happen. Like waiting for a key press, a file to load, or a message from another process. The scheduler manages this table. It adds new processes, removes finished ones, and decides who gets to run next. But deciding who runs is one thing. Actually running them is another. That's the job of the dispatcher. Here's how the dispatcher works in a time-sharing system. It divides time into tiny time slices, typically measured in milliseconds or even microseconds. It lets one process run for one slice. Then it switches to another, then back to the first. The switch is called a process switch or a context switch. How does it know when a slice is up? It uses a hardware interrupt, a signal from a timer chip that says, "Time's up." When the CPU receives an interrupt, it immediately stops what it's doing, saves its current position and state into the process table, and jumps to a special program called the interrupt handler, which is the dispatcher's way of saying, "Okay, who's next?" Think of it like a chef in a kitchen. They've got 6 dishes cooking at once. Every few minutes, a timer goes off. They check on one dish, stir something, move to the next. No single dish has the chef's full attention, but everything gets cooked. The beauty of multiprogramming is that it increases efficiency even though it sounds complicated. Here's why. If a process is waiting for a file to load from disk, that takes hundreds of milliseconds. Without multiprogramming, the CPU just sits there, twiddling its thumbs. With multiprogramming, the dispatcher says, "Cool, you're waiting. I'll let someone else use the CPU while you wait." Way more efficient. All right, let's get concrete. Let's talk about what happens when processes compete for resources. And 2 really important concepts, semaphores and deadlock. Imagine 2 processes both want to print at the same time. Your computer only has one printer. If both processes get access simultaneously, they'll send output to the printer at the same time, and you'll get garbage. Scrambled, interleaved nonsense. So the OS needs a way to say, only one process can use this printer at a time. The solution is a semaphore, one of the most elegant ideas in computer science. A semaphore is basically a flag. It can be set, value 1, resource is in use, or clear, value 0, resource is free. Before a process uses the printer, it checks the flag. If it's clear, great. It sets the flag and uses the printer. If it's set, it waits. When it's done, it clears the flag so someone else can go. The term semaphore comes from railroad signals, those flag systems used to control which train could enter a stretch of track. Software semaphores work exactly the same way. There's a critical subtlety here, though. The act of checking and setting the flag has to happen as one uninterruptible step. Otherwise, a sneaky interrupt could allow two processes to both check the flag, both see it's clear, and both grab the resource simultaneously. That's why modern CPUs have a special instruction called test and set. It reads the flag and sets it in a single atomic operation that can't be interrupted. The section of code that uses a shared resource is called a critical region. The rule that only one process can be in a critical region at a time is called mutual exclusion. Now, here's a fun one. What happens when two processes are each waiting for something the other one holds? Process A has the printer and needs the scanner. Process B has the scanner and needs the printer. Neither will give up what they have. Neither can proceed. They're stuck forever. This is called deadlock. It's exactly like two cars meeting on a one-lane bridge. Neither will back up. Neither can go forward. Traffic stops. For deadlock to occur, three conditions must all be true. 1. There's competition for a resource that can't be shared. 2. Processes request resources one at a time. They hold some while asking for more. 3. Once a resource is given, it can't be forcibly taken back. To prevent deadlock, you break one of those conditions. Some strategies require processes to request all resources up front. You can't hold some and ask for more. Breaks condition 2. Allow forcible retrieval. The OS can kill a process to free its resources. Breaks condition 3. Make resources appear shareable. For example, instead of connecting a process directly to the printer, you send output to a temporary file, and the OS prints it when the printer is free. This technique is called spooling. Spooling is actually something you use every day without thinking about it. When you hit print and your document goes into a print queue, that's spooling. The OS is managing shared access behind the scenes. What about multiple cores? Modern computers have multi-core processors, multiple independent CPUs on a single chip. Your laptop might have 8 or 16 cores. This means processes can actually run in parallel, not just take turns, but it makes competition management harder. You can't just disable interrupts to protect a critical region, because another core might be running a competing process at the exact same time. Computer science researchers are actively working on better mechanisms for multi-core systems. It's an open, exciting area. Let's bring it all together. What is an operating system? It's the software manager that coordinates your hardware, runs your programs, and makes the computer usable. Without it, you'd be flipping binary switches. How did we get here? From batch processing in the 1950s, one job at a time, to interactive processing, to time sharing, to modern multitasking OSEs that juggle dozens of processes per second. What's inside? A user interface on the outside, shell or GUI, and a kernel on the inside, containing the file manager, device drivers, memory manager, scheduler, and dispatcher. And the bootloader gets the whole thing started when you hit power. What's a process? It's a running program, a dynamic, living activity with its own state, memory, and priority. Modern computers run many simultaneously. How does it work? Time slices, context switches, and interrupts. The dispatcher gives each process a brief turn, rapidly switching to create the illusion of simultaneous execution. What about competition? Semaphores prevent two processes from colliding on shared resources. Deadlock happens when processes block each other in a circle, and smart OS design prevents or resolves it. This stuff runs invisibly under everything you do on a computer. Every app you open, every file you save, every time your machine smoothly handles 10 things at once. That's your operating system doing its job. If you want to go deeper, try opening Task Manager on Windows or Activity Monitor on Mac. You'll actually see the process table. Dozens of processes you never knew were running. It's a whole world under the hood. Thanks for watching. See you in the next one.